We want to welcome you to the Dallas Independent School District STEM Environmental Education Center virtual field trip. We want to say a very special welcome to David G. Burnett, Gay P. Allen, Urban Park, Arthur Kramer, Stevens Park, and Martin Weiss, all of the Dallas ISD. Teachers, if you're watching and you're not signed up, please go to www.tiny.cc/3-5 registration and sign up. The program this morning will be about forces. During this virtual field trip, students will investigate the effect of forces on an object. Ms. Schramm will discuss magnetism. Gravity will be covered with Mr. Monroe. Mr. Maris will do pendulum investigation, and friction by Mr. Dominguez. During this program, you cannot ask us a verbal question, but you can go to www.tiny.cc/question-answer and fill out a form. And now I'm going to stop sharing my screen. And Mrs. Schramm is going to tell you all about magnetism.
Hey everybody, it's Ms. Schramm. And like Dr. Gorman said, I'm talking all about magnetism today. So at the end of my little section, you'll be able to design simple experiments and investigations that test the effect of magnetic force on objects. So before we get going on magnets and other objects, I want to explore how magnets interact with one another. So the magnet that we're going to use right now is a bar magnet. So you'll notice the one I have in my hand, as well as the one that's on the screen, has a red side and a blue side. So the red side has an N and the blue side has an S. That is for the North Pole and the South Pole. So every single magnet has a North and South pole, but these ones are labeled because they're designed for classroom use, so we know what pole we're working with. So first, I want to see what happens when I bring different poles together. So the first one is going to be two North poles together, then a North and a South pole together, then two South poles together, and we'll see what happens. So let's go to the work table. And I have my North pole facing in. And I'm going to bring another magnet here with the North pole facing in, and we're going to see what happens when they get close. So that North pole is pushing the other North pole away, and it's making it even turn around. And if I hold them close together, I can feel the magnetic force between them pushing them apart. That is called repelling. So two North poles repel each other. If I flip it over, I have the South pole facing the North pole. If I bring it close, it is attracted to each other and it's able to pull it along. So I can feel them attracting to each other. I'm sorry guys, I dropped it. But they almost like snap together. All right, now we're gonna try a South pole and a South pole. So based on what happened in the last two, I want you to be predicting. What do you think is gonna happen when I bring two South poles together? It pushes it away. So two South poles repel each other. They push apart. All right, let's look at our little chart and see what we can find. So when we bring two North poles together, they repel each other. When we bring a North and a South poles together, they attracted each other. When we bring two South poles together, they repel each other again. So the pattern is that two like or two similar poles will always repel each other, and opposite poles will attract. All right, so we're going to use that knowledge in a little bit, but let's first talk about the magnetic field. So the magnetic field is the area around the magnet that is affected by the magnet. So the larger the magnet, the larger the magnetic field. These little bar magnets have a relatively small magnetic field. As you could see, it took a little while for the magnets to interact. I had to bring them quite close, so it's not too big of an area. So since we can't see that magnetic force and we can't see the magnetic field around the magnet, scientists use iron filings. So in the picture on the left, someone took pieces of the metal iron and shaved off little tiny bits. So it's like glitter. And they sprinkled it around the magnet to kind of show the pattern of the magnetic field. So you can see at the poles, there's a larger concentration of iron. So all those little filings are attracted to the poles. Then they kind of form lines around the magnet. And then as you get further away, those little particles were not affected by the magnet. So they're just scattered randomly. And then a little more clear diagram of how that magnetic field would look if we could see it is on the right. All right, so here are some examples of magnetic force that we see in our lives every day. We have compasses, which we'll talk about in a second. Then the next example is a maglev train, and those trains actually use magnetic force to propel them forward. So they're constantly being pushed and pulled by changing magnetic poles underneath the tracks. Then we have computers, speakers, all different kinds of technology use magnets inside. Electric motors use magnets. When you go to the doctor's office, a lot of the machinery, like an MRI machine, use giant, powerful magnets. And even in your kitchen, appliances like refrigerators, microwaves, all use magnetic technology. So now let's get to the fun part. We're going to do some little experiments with magnets. So I made a little, excuse me, my cat is sitting on it. I made a little, I can't think of the word, pendulum. Haha. Mr. Ramirez is going to teach you about those in a little bit. But anywho, I put a paperclip on a string and it swings back and forth like a pendulum. So I can make this paperclip stop moving or start moving just by using magnetic force. Because the paperclip is attracted to a magnet or the magnet is attracted to the paperclip, I can make it move. So let's see, if I bring my magnet close, all right, I can swing it back and I can make it stop. Boop. And either side works because the paperclip itself is not a magnet, so it doesn't have poles. It is just magnetic. Magnet is attracted to it. All right, boom. First example under our belts. So now we're going to talk about compasses. So compasses use magnetism to tell us what direction you're traveling. It might be hard to see, but there's little letters that say NSEW, north, south, east, west. So that tells you where you are traveling. Now, the red arrow always points north. So this one's a little wonky because it's been sitting in my magnet box for a while and I'm not holding it correctly to tell me direction. But the red arrow points to the Earth's North Pole, the Earth's magnetic north. The Earth is one giant magnet. So like I said earlier, the magnetic field gets larger as the magnet gets larger. So obviously you could assume the Earth has a huge magnetic field. And the compasses use that magnetic field to tell you what direction you're going. But if I bring a smaller magnet, I can kind of manipulate which way the arrow points by interfering with that magnetism, right? So this magnet has a small magnetic field, but if I bring it close, it will interact with the compass. So I can bring it close, and sure enough, I can make the magnet or the compass turn. If I flip my magnet, I can flip the arrow. Boop. Let's see. Oh, now I still want to. I told you this one's wonky because it's been sitting in my magnet box for a while now. But either way, I can manipulate the arrow using my little magnet. Boop. There we go. All right. So now I wanted to show you some of those iron filings we talked about. Hold on a second. I hate to tell you this, guys. My dog just stole my lunch live on camera. Oy, oy, oy. Okay, anywho, magnets. Oh, you're going to pay for that, Leroy. Okay, so this iron filings is like what I showed you earlier. And they are attracted to the magnets. So when I bring my magnet underneath the iron filings, let's see what happens. You can kind of see them, they almost start to like stand up. And I can move them and drag them around. All right, and you can move them all over the place. All right. Next, I'm going to make my little toy car move without touching it. So I've taped a little bar magnet to the top of my little car, and I'm going to use my bar magnet to push and pull the car forwards and backwards. So I'm going to set my little car down, back to the work table. And let's see, I'm going to bring my magnet close. And using what we learned earlier, I can make it go forwards or backwards. So if I have a south pole in the back and I want to push it forwards, I'm going to bring another south pole of a magnet in the back to push it forwards. Now, it definitely moved it. It doesn't go exactly forwards because my tape got kind of scrumpled up in the wheels. But either way, it does move it forward. So then if I wanted to pull it forward, I will put my south pole of the magnet in the front and pull my car forward. All right. So my challenge to you is to look around your classrooms or look around after school at your house or when you're at the store and try to see different examples of magnetic objects in real life. All right, I hope you had a good time and I will see you next time.
Thank you, Ms. Schramm. Question came in. What are the characteristics of magnetism? There are three of them. They are attractive property. Magnet attracts ferromagnetic materials such as iron, cobalt, and nickel. Repulsive properties. Like magnet poles repel each other, and unlike magnet poles attract each other. Directive property. A freely suspended magnet always points in a north-south direction. And now Mr. Monroe is going to introduce a subject called gravity.
Okay, good morning, students. My name is Mr. Monroe, and we're going to be looking into that force that holds everything in place on our planet called gravity. It keeps us from floating away, right? Well, they give credit to an outstanding scientist who has come up with a variety of laws or rules that deal with motion. His name was Sir Isaac Newton. And Sir Isaac Newton, one day, I guess he was really, his mind was working. He was thinking about forces of nature. And he just so happened to be near an apple tree, according to this legend. Now, observing the apple tree, he noticed an apple fell from the tree. Now, when I was in elementary, it was taught, or the legend said, that the apple actually hit him on top of his head. But whether it hit him on the head or not, or whether it hit the ground, that doesn't matter, because it made Sir Isaac Newton realize that some force must be acting on falling objects. Otherwise, they would not start moving from a position of rest. And so he came up with gravity. Now, gravity, not only does it pull things toward the center of the earth, according to Sir Isaac Newton, but everything that is made up of matter has a bit of gravitational pull to it. He concluded that the larger the matter, the larger the mass of an object, the stronger the gravitational pull. And even came up with the conclusion that objects that are distant from one another, their gravitational pull between those two objects, if there's quite a bit of distance, that strength of gravitational pull is weaker or weakest. Now, I guess a perfect example would be like if we launched a spacecraft from the planet Earth, and that spacecraft was headed to Mars. Well, of course, the gravity of planet Earth would be affecting that spacecraft until it got quite a bit of distance from the planet Earth. And the closer it got to the planet Mars, the gravitational pull of Mars then would become stronger, and that spacecraft would have lesser resistance in trying to get to Mars, okay? Now, students, listen. Gravitational pull, according to Sir Isaac Newton, pulls things down toward the center of the Earth. And there's a tendency for it to accelerate the closer it gets to the surface of our planet. Probably he observed that when the apple fell from the tree. Now, I've got a ball up here hung on this board here, and it's taped. And if I release it from the tape, it fell. Gravity pulled it down. Now, I couldn't really tell whether it got faster as it got close to the floor, but I imagine it did according to his law. But I will tell you this. It resembled that apple falling from that tree. Now, the gravity actually was an unbalanced force acting on that ball. Take, for example, this large book. Right now, the forces that are holding this book in place are what we consider balance. Of course, we know that gravity is pulling it down, right? And of course, my hands are underneath it, keeping it from being pulled down. So right now, it is affected by a balanced force. It's not going anywhere. It's at rest. But if I release my hands out from under it, it becomes a subject or an object being pulled by gravity, which is an unbalanced force. Just like that, okay? Gravity acted as an unbalanced force there. And you know what? You heard me say that Sir Isaac Newton believed that all objects are attracted to each other. And the reason that we don't really feel that is because of the Earth's gravitational strength, okay? It's much more. Now, you all are fifth graders. And fifth graders, sometime this year, are going to be studying Earth science. And when you study Earth science, you're going to be studying about Earth processes. These are processes that happen to our planet that may even change our planet physically. There are several Earth processes like weathering and volcanoes and earthquakes. Those are things that might change our planet's surface, and it would be very observable. There are other processes such as erosion, and we see that constantly. Now, it is said that water in concert with gravity is the strongest erosion agents that we have here on the planet Earth. I have prepared a stream table for you to observe. And I'm going to create a scenario where at the higher elevation, which is up here, let's say that this is the side of a mountain or a mountain range. And the scenario is this, that we get so much rain at the higher elevation that it causes flooding up at the higher elevation. And then gravity starts pulling the water down to the lower elevation. Now, it is said that if gravity is acting on a force going downward, if the action or the object of that object is moving downward, if it's moving downward more than 2 seconds, it's beginning to speed up. Every 2 seconds, whatever's being pulled down by gravity, guess what? It is accelerating. So that kind of explains why it speeds up when it starts really getting close to the lowest part or to the floor or to the ground. So let's see what happens. Now, also in the fifth grade, you guys are probably going to be studying about landform. And erosion causes landforms, certain landforms to develop. Here we go. Going to pour a little water right down the middle. And what we've done, we've created a riverbed. Here we have a deep crevice here. And this deep crevice, it could be a canyon. And if you know anything about the Grand Canyon, that's how the Grand Canyon was formed. And we have a riverbed, and at the end of the riverbed, where the land begins to flatten out, begins to level out, we have another landform that we call a delta. Let you guys look at that. Okay, so water and gravity in concert with each other actually is the strongest erosion agent on the planet Earth, okay? Now, it is said that one of the things that drives plumbers crazy, guys, is the fact that if there is a leak, a plumbing leak where there's water involved, it's very hard sometimes to find where the leak is because water is going to move to wherever gravity is going to pull it. It may run a little ways when it's leaking out of a leak and then go down wherever it can. It's searching for a place so that it can actually become part of the gravitational pull that's going on. Now, let's talk about the solar system. One of the things that I want you guys to understand is why our solar system's actions are like they are as far as all the planets moons, they are revolving around the sun. And that's because of gravity. Here I have a model of just our sun, our planet, the Earth. Let me get that around, get that on screen. And our moon. Well, it is said that our sun is so massive, it exerts a very strong gravitational pull that affects all the planets that exist in our solar system. And that's why they all revolve or orbit around our sun, simply because of the strength of the gravitational pull from the sun. Now, as far as the planet Earth, it has a strong gravitational pull that is affecting our moon. It holds it in an orbit around our planet. It is said that the sun is about 28 times stronger in gravitational pull strength than the planet Earth. And the planet Earth, because of its size, remember, the more the mass, the stronger the gravitational pull. Well, the planet Earth is it has about 8 times the gravitational strength that the moon does. So if you were on the moon, oh man, you wouldn't weigh as much, and probably it wouldn't take much for you to maybe a high jump over 10 to 12 feet, because the gravitational pull would allow you to really jump very high, maybe too high. You could injure yourself. We don't know. But listen, it's a lot less than what the planet Earth's gravitational pull is, simply because of the amount of mass that it has. Planet Earth is much larger than the moon, and the sun indeed is much more massive than the planet Earth and most of the planets that exist, in fact, all of the planets that exist in our solar system. Now, how does gravity affect living things? Well, we know how it affects us. It holds us in place. You know, without gravity, we'd be floating all around this place. But we're kind of fixed. Now, we do have the ability, because of that gravitational pull being not so strong, that we can walk and we can run and we can jump a little bit. So just think, if the gravitational pull was stronger, we might have a hard time doing that. Even plants, if you really think about it, plants, their roots grow downward, right? And on the stem, we've got branches out and leaves. Those leaves kind of have a tendency to grow upward. We know, well, of course, they need sunlight, and then we know that the sun is above them, so they're going to be stretching toward the sun. But guess what? they're also being affected by gravity. Because if they don't get that sunlight, they're going to droop. And those leaves that are drooping, how are they going to be? They're going to be going down. But other animals are affected by gravity. Take birds, for example. A lot of birds, they fly from place to place. And no doubt, the pull of gravity will cause them not to be able to fly as far as they would like to because they're going to get tired and they're going to land. The other day, I had Bessie the quail out, and I wanted the students to see Bessie fly. She was going to be flying, proving that she could deal with gravity to a certain extent until she got tired of flying. Well, immediately she flew off the desk here and landed on the floor. Well, I was afraid she had hurt herself, so I didn't try that anymore. But I do have another animal I'd like to show you. This is Hoppy the bullfrog. Now, Hoppy the bullfrog, he goes airborne too. And you know, they say what goes up has to come down because of gravity. Well, that's true in this case. He's got these big muscular legs and these big old wide feet, web feet, as platforms to spring off of. This guy can jump. Oh man, if I put him on one side of the room, he could probably jump half the distance between. But eventually, guess what? He would have to come down because of gravity. Well, students, listen. I hope I've helped you learn a little bit about gravity today. Very important force that exists on our planet. I'm going to turn it back over to Dr. Gorman in case some of you have questions. I bet he can answer them for you. I want you guys to have a good rest of your virtual field trip today.
Thank you, Mr. Monroe. And we did have a question. Where is gravity the strongest in the United States? In general, the closer the center of two objects, the greater the force of gravity becomes. Therefore, you would expect gravity in the United States to be stronger wherever you are closest to the center of the earth. Now, I have happened many years ago to be in this place. It's not a very hospitable place. In fact, you really wouldn't want to live there unless you love heat. It's called Badwater Basin. It's in Death Valley out in California. It is 282 feet below sea level. And now, Ms. Ramirez is going to tell you about pendulums.
Hello, my name is Ms. Ramirez, and in this segment, we're going to be learning about pendulums. Pendulums are simply swinging objects. So I have an animal friend that's going to help introduce us to pendulums. I'm going to give you some clues to who this animal is, and then I'll let you guys guess. So this animal friend is a mammal, so his body is covered in hair or fur. This animal friend loves to play with this swinging pendulum toy. So this animal, he loves to chew on these toys and he likes to push and play with these swinging objects. This animal has long ears. This animal is an herbivore, and this animal can run and jump rather quickly. So go ahead and make your guess to who you think this animal is, and I'll go pull him out. If you guys guessed a rabbit, you would be correct. So this is my newest rabbit. This is Pfeiffer. We know that he's a mammal because he is covered in fur, and because his teeth continuously grow, he loves to play and chew with his swinging pendulum toys. So I'm going to go ahead and put Pfeiffer the bunny up, and we'll continue on. I actually have a quick little video that I'm going to share with you guys, and it's of one of my other rabbits, Baby Bunny Lucky, playing with a pendulum. So here we have a swinging pendulum. It's simply a bell that's been tied to a string and it's swinging. So that swinging motion is because, if you notice, the rabbit is applying a force. Baby Bunny Lucky is pushing the bell with his nose, and that force is causing the bell to move. Now it's going to continue to move because of gravity. So gravity is what is trying to pull that bell back down. Now, also we have what's called inertia. Inertia is just the tendency of an object to stay in motion, and it's going to stay in motion unless another force stops it. In that case, we know that the force that stops motion is called friction, and you'll learn about that later on today. So let me get rid of that video and we'll continue on with our pendulum. So think of an example of a swinging object out on the playground. Super easy. So an example would be the swing set. So when you guys are on the swing set, that swing is a pendulum that is using gravity to pull you back down from your high point. Now, eventually, you're going to slow down and stop swinging altogether because of friction in the form of air resistance. So those are some of the forces that are in play when we talk about our pendulums. Now, a quick little history behind the pendulum. The story goes that in the 1500s, a scientist named Galileo was sitting in church and he happened to notice that the chandeliers were swinging back and forth. Now, he noticed sometimes they were doing these really big swings and sometimes they were doing little swings. And he wondered, why is that? Now, being the good scientist that he was, he actually created his own experiment to study the swinging motion of objects. We now know Galileo as the father of experimental science. Now we're actually going to create our own little experiment with a pendulum, and we're going to be answering this question. So the question that we're going to be looking at today is, how does the length of a string affect the number of times a pendulum will swing? And we're actually going to do it in 15 seconds for time. So we're going to fill out this chart as we work through our experiment. So let me show you the pendulum. So some parts of the pendulum, we have this top, which is the support base. Attached to the support, we have the string. The science word for this part of a pendulum is called the arm. And then at the end of the pendulum, we have the swinging weight. The science name for that swinging weight is called a bob. Now I have 3 different string lengths. So again, we're going to be trying to learn, how does string length affect the number of times a pendulum will swing in 15 seconds. So we have a short string that's 5 centimeters, a string at 10 centimeters, and a long string at 20 centimeters. So go ahead and make your guess. What string length will swing the most times in 15 seconds? Teachers, feel free to pause the video to allow students time to discuss their hypothesis and also to maybe explain why they think that way. And I just want to go over briefly the motion. So again, I'm going to apply a pull. I'm going to apply a force. In this case, it's a pulling force. I'm pulling the pendulum back. When I release it, gravity is the force that is trying to pull it back down. And even though I'm no longer touching it, it is still moving because of inertia. So remember, inertia is just the tendency of an object to stay moving until something stops it. In this case, we know that that something is friction that is stopping our little pendulum from moving again. So the way we're going to count it, 1 full swing is denoted as the time it takes to get back to the original position. So if I pull it and I start here, when I drop it, it's going to go forward and then it's going to come back. When it gets back to where it started, that is 1 full swing. And I'm actually going to put my hand behind it and I will count out loud each full swing because I know it's kind of hard to see on the computer screen. So hopefully you guys have your hypothesis for which one you think will have the most swings. I'm going to start my timer for 15 seconds. Go ahead and give a quick guess really quick. How many times do you think the 5 centimeter string will swing in 15 seconds? So make your guess really quick. I'm going to apply my force. I'm going to pull it up. And then when I drop it, gravity is going to do its thing and it's going to cause it to pull back down. So let me start it and we're going to count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26. Oops, and there's our timer. So that was about 26 swings. So I'm actually going to write that down. Let me find my marker. I'm going to write that down. 26 swings for the short 5 centimeter string. Make your guess. How many times do you think the 10 centimeter string will swing? Make your guess. I'm going to apply my force. I'm pulling it up. When I release it, gravity will do its thing and try and pull it back down. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. Oops, there's our timer. So it's about 22 swings for that middle one. So far we have 26 swings, 22 swings. Now make your guess. How many swings do you think the long string will have in the 15 seconds? Hopefully you guys are starting to notice a pattern. So make your guess. Again, I'm pulling. I have applying my force. I'm pulling it. Gravity is going to do its thing. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 7. There's our timer, 17. It did hit the side, but that shouldn't affect it too much. So about 17. So hopefully you guys are able to see that yes, string length does affect the number of swings for our pendulums. So the longest string only had 17 swings. However, the shortest string had the most swings at 26 swings. So we do know that yes, the string length will affect pendulum swings. So a good scientist would repeat this experiment at least 2 more times to get good results. But since we're almost out of time, I'm going to let you guys finish this at home. And to do this at home, you can make your own pendulum. All you need is a pencil, a piece of string, and then maybe a paper clip. And you guys can experiment with different string lengths. You can also see how your pendulum is affected by different weights at the bottom. So right now I have a very light paper clip, but what happens if you were to tie something heavy and go ahead and start the swinging experiment again? Also think about, well, what happens if I drop it from way up here versus what happens if I drop it from further down? How does that impact the swinging motion of a pendulum? So again, go home or at school and try your own pendulum experiment. That's all I have for you guys for motions that affect swinging objects. We're going to give it back to Dr. Gorman to answer any questions.
Thank you. Excuse me. Thank you, Ms. Ramirez. The question is, what are pendulums used for? A pendulum, body suspended from a fixed point so that it can swing back and forth under the influence of gravity. Pendulums are used to regulate the movement of clocks because the interval of time for each complete oscillation, called a period, is constant. Thank you again, Ms. Ramirez. And now Mr. Dominguez is going to tell you all about friction.
Hey guys, today we're going to be talking about friction, and friction is a force that occurs when two objects rub against one another, their surfaces. And right now, as I pull this block, there is friction. However, my pull is a stronger force. It's overcoming the force of friction, therefore I have movement. However, if I were to pull and just let go, friction stops this object from moving. So today we are going to do a little experiment that explores how the texture of different surfaces affect friction. So let's get started. All right, guys, the goal of this experiment is to answer the question, does surface texture affect the amount of friction exerted on an object? And my hypothesis is that yes, the rougher a surface, the higher the force of friction, and the smoother the surface, the less friction that will prevent an object from continuing its motion. So let's get started with the experiment. All right, guys, for today's experiment, you will need a few items. Some of the items you can find around your classroom or home. If not, you can find them at any local hardware store. You will need something to make an inclined plane with, something with a flat surface. I chose this piece of 2x4, but you can use anything else with a flat surface, as long as you can move it up and down. You're going to need another object with a flat surface. So this is a flooring sample from my local hardware store. It's free. You're going to need some tape, some sandpaper, some copy paper, some aluminum foil, and something to measure height with. So I have this measuring tape, but you can use a ruler. Either one is fine. And a partner, because having a partner makes things easier. So remember that the purpose of this experiment is to determine whether the roughness or the smoothness of a surface will have an effect on friction. My hypothesis states that the rougher the surface, the more friction there will be, and the less inclined, get it, an object will move. So the less inclined an object will be to move. And the smoother the surface, the more easily that object will move, okay? So the way we are going to measure that is simply by measuring the height at which the object, and in this case, it's going to be this object. So at what height this object begins to move. At that point, I will know that gravity has overcome the force of friction and made this object no longer stationary, but, kinetic. So what we're going to do first is we are going to measure this surface right here. So we're going to measure 4 surfaces: the wood surface, the sandpaper, the copy paper, and the aluminum foil. And we're not going to measure the angle or anything of the inclined plane. All we're going to do is we're going to measure the height. We're going to keep it simple. So let's go ahead and let's get started. And make sure that your object since this object has 2 different types of surfaces, I got to make sure that I always use the same surface. You want to keep the variables at a minimum so your variability isn't too high and your results are all over the place. So let's test out this surface first, the wood surface. And remember, your surface might be different. You might have chosen to use your journal or something else, but for me it's this wood surface. So remember, I am going to lift this up until it begins to move and gravity begins to take over and friction is no longer the dominant force. So, there it started moving. And I'm going to try my best to keep this still. That's why I said this is easier with a partner. So let's measure this. I hope I don't move it too much. Let's see. That is about, and I'm measuring from the bottom. So that is 10 inches. So that is 10 inches of height before my object started moving. So wood surface, 10 inches. All right, so let's test out what I think will have a dramatic effect on friction. So I think this will create a lot of friction because it's the roughest surface. So I'm going to use the tape to fasten this down. So let's see. And while I set this up, you guys can make your predictions. So what do you guys think? So it was 10 inches of height for the wood surface. How much height do you guys think I'm going to need to get this object moving? So let's find out. All right, so let's lift. So we're still lifting. That was a lot of height. So let's measure that. So let's see. That was 18 inches, guys. So 18 inches of height. So there was a lot of friction, wasn't there? All right, so let's test out our other surfaces. So far we have 10 inches for the wood surface, 18 inches for the sandpaper. So 10 and 18. And make sure I don't have my journal with me right now, because but you should be writing your results down. And of course, good science tells us that we should have multiple trials. So try, and try, and try, and try again. All right, so copy paper. So remember that the wood surface was 10 inches. the sandpaper was 18. So 10, 18. Now let's try the copy paper. And it feels pretty smooth, but it feels pretty similar to the wood surface, so not much of a difference. So let's test this out. So I think that the copy paper will give me a similar result to the 10 inches of height that I needed to get moving with this wood surface. So let's try this. Okay, there it goes. Let's measure that. That is 9 3/4, so very close to 10 inches. So like I said, it felt pretty similar. So the surfaces, they feel pretty similar. So I was expecting a similar result. And lastly, we have the aluminum foil. And let's make sure that we get this nice and flat. Because I noticed that there's some crinkles, and that might affect the friction between the aluminum's surface and this surface right here. So I want to make sure that it's nice and flat like the other ones were. All right, so make sure we secure this so it doesn't move. All right, so now they feel similar. In fact, this actually feels a little bit stickier than the wood surface, and it just does. I thought this would be a lot smoother than the copy paper and the wood surface, but it's not. It actually feels a little bit in a way stickier. Just my fingers are sticking more to the aluminum than they are to the wood. So I think that we are going to get something that is maybe more than 10 inches for the aluminum. So let's find out. All right, so let's see. We're going to lift this until it starts moving. So there it goes. So let's measure that. Try to be as accurate as possible, but this is better with a partner. So this was about the same. It's about 10 inches. So it was a smooth surface, but to my fingers, it felt a little bit stickier than both the wood surface and the copy paper, but still pretty smooth. Now, I think this proved my hypothesis correct, because this rough surface took a significant amount of height to get this object moving. So, I hope that you guys learned a little something about friction today. I hope that you guys test your own surfaces and test what surfaces give you the least amount of friction, what surfaces give you the most amount of friction. And I hope you guys have a good discussion about why having a lot of friction can be a good thing, why it's a bad thing sometimes, and also the opposite, why having little friction can be a good or bad thing. All right, so I hope you guys have a wonderful day. I will see you guys next time for our next experiment.
Thank you, Mr. Dominguez. We did have a quick question. What might happen if there's no friction? You will not be able to ride, no riding a bicycle, bike, or even a car or a bus. No machines in company, so no mechanics. You would have not been able to sit, walk, run, or dance. And now I'm going to share my screen. During this virtual field trip, students investigated the effect of force on an object. Ms. Ram discussed magnetism. Gravity was covered by Mr. Monroe. Mr. Ramirez told you about pendulums, and Mr. Dominguez discovered friction. Thank you. If have been watching this, please go to www.tiny.cc/3-5 feedback. Fill out a very short form and send it back to us. We certainly